So hello students, childrens, today we are going to study a topic in colligative properties, and in that we will be studying lowering of vapor pressure, elevation of boiling point, depression of freezing point, osmotic pressure. सारे वर्ड्स सर नए नए लग रहे हैं. All the things are new, but don't worry childrens, we will be taking one topic at a time, and we will start from what is the meaning of colligative properties. First we will understand what is colligative properties. Thereafter we will be discussing each of these 4 points one by one. So childrens, colligative, actual it means collective effect. नहीं समझा सर? Take an example. If suppose a crowd of 1 lakhs of people moving on the road in one direction, definitely everyone is going to notice it. Everybody will think what is going on. This is the one scene. Entire media will cover it. It will come on the headlines. All these things will happen. People will take the notice. Why this morcha is going on? Okay. Second scene. One person moving on the road. Nobody will notice him. Right? Dear children, when large number of particles are coming together, then they are having some unique impact, which is known as the colligative property. Which is known as what? Colligative property. Children, according to psychologists, a crowd is more dangerous than the single individual person. A crowd, a mob, which is moving on the road, he may turn out violent, he will be more dangerous in that scenario. But same person of that mob, if he is moving alone, he will not behave in that way, or his impact will not be up to that extent. This tells you what is the difference between one particle and large number of particles. So, we are going to study effect of the particles, large number of the particles on the properties of the solvent. If suppose I am taking a solute particle, it may be sodium chloride, ionic particle. It may be urea, which is not going to ionize. So, we will be restricting ourselves up to the non-electrolyte solute. Now children, any solution is consist of 2 parts, solvent and solute. Solvent, for example, I am taking water. I have taken water as what? Solvent. This water is the solvent. Now for solute, there are 2 cases. If you are taking urea or you are taking sodium chloride, children, number of the particles which we are putting in the water, they will produce different impact. Normally we know boiling point of the water is 100 degrees centigrade. But children, if you add sodium chloride to that, if I am adding sodium chloride to what? Water. It will not boil at 100, it will be bit higher. Boiling point will be increased. Now children, this impact is just because of what? Because of number of the solute particles. Instead of sodium chloride, if I am adding urea, then also the same impact will be observed. What does it tells us? Children, it tells you that this property, that what is that property? Elevation in the boiling point. Increase the boiling point. We are using a specific term, elevation. Elevation in the boiling point has nothing to do with the chemical existence of the particle. Its chemical nature. Whether you are taking sodium chloride or you are taking urea or you take any other substance, what matters is only number of particles. What is important is the number of particles. Children, you know that sodium chloride is having a tendency to split into ions. When we dissolve sodium chloride in the water, it will split into what? Ions. And it has been found when 1 mole of sodium chloride and 1 mole of urea, when we dissolving in the water, elevation of the boiling point in case of sodium chloride is double to that of the urea. Can you find the reason for this? Can you tell me what is the reason for this? Because colligative property depends on the number of particle and not which particle you are dissolving. When we dissolved sodium chloride in water, it got split. We were thinking that we are dissolving only 1 mole of the sodium chloride, but children, in reality, inside the water, there were 2 moles of the particles present. And when you dissolved urea, urea is a non-electrolyte. Urea is a non-electrolyte. It cannot split in the water. So, when we are dissolving 1 mole of the urea, it remains 1 mole. But the thing entirely changes when we are dissolving sodium chloride. In case of sodium chloride, what happens? You are dissolving 1 mole. You think that you are dissolving 1 mole, you have written in your paper that 1 mole, but when actually sodium chloride enters in the water, it got split. And it acts as there are 2 moles. So definitely 2 moles of the particles will cause a different impact. If you want to get the same impact in case of urea, and it has been observed that when 2 moles of the urea were dissolved, then impact was same as we were finding in sodium, 1 mole of the sodium chloride. So it has proved beyond doubt that colligative property depends only on the number of particle and not on the nature of particle. Now children, at the initial stage of our study, we will restricting ourselves only up to the non-electrolytes. So there will not be any confusion that how many particles will be there inside the water. If we are adding 1 mole, it will remain 1 mole. So sodium chloride we are not going to use the electrolytes. So in all our discussions, all the solutes what we are now going to use will be non-electrolytes. So this is out of our discussion for the moment. And hope children, now you have understood what is the colligative meaning. What is colligative property? What is the meaning of this colligative property? In next video children, I will be discussing with you lowering of vapor pressure. So see you children in the next video. Thank you. So hello students, let's continue with the topic of lowering of vapor pressure. Children, lowering of vapor pressure, before studying this point, let's try to understand what is the meaning of vapor pressure. Right? Vapor pressure means what? पहले तो हम ये समझेंगे आज. So let us see. Children, you take any liquid you take of your choice. Every liquid is having a property of getting evaporated at the room temperature. You take a plate, put the water over there, observe it after 1 hour, 2 hours, its level will reduce. Next day, almost everything will be gone. Children, what it tells you, this phenomena, this thing is telling that liquid was volatile. Every liquid is volatile. Only thing that it may be more volatile, it may be less volatile. Ethyl acetate, highly volatile. Water, it's also volatile. Engine oils, what we are using, they are also volatile. They also evaporate, but only to a very small extent. Children, all the particles of this liquid, they will hold each other. That is known as the intermolecular forces. That is known as what? Intermolecular forces. A force which is acting between two molecules. Now, these molecules are present here. They are bonded to each other. And this force of attraction, which is holding these molecules together, is known as intermolecular forces. Known as what? Intermolecular forces. If suppose children like engine oils, These forces are very strong in that case. Lubricants what we are using for the vehicles, these forces are very strong. Hence they get volatile they get evaporated to a very little extent. But if I am taking water, but if I am taking ethyl acetate and all, if I am taking acetone, then their intermolecular forces are very weak. Hence, particles which are there on the periphery, on the upper region, particles which are present on the upper region, they absorb the energy from surrounding and they got evaporated. They leave the system and thereafter new layer. Slowly entire this liquid will get evaporated. This now suppose I am taking a liquid which is volatile in the nature, and if I am putting a cover on this, suppose I am covering it, means no particle is allowed to leave the system. Now what will happen? The particles which are there on the periphery, on the upper region, after absorbing the heat energy, they will get evaporated. They will come in the vapor form. Gaseous form of any liquid is known as the vapour. Gaseous form of any liquid is known as what? Vapour. So this liquid has come now in the vapor form. After evaporation, a reverse process starts. Means these particles from the vapor again go through the process of condensation. They come back. And the particles which are leaving the system, they are following a process of evaporation. Since it is entirely closed, hence children, soon there will be an equilibrium. At the stage of equilibrium, number of the particle leaving the system and number of the particle entering the system, that entirely remains the same. Whatever number are leaving now, same are entering. But in other case, suppose I am taking the liquid and I am not covering it. Particles which are coming out in the vapor form, they will be dragged away by the air. Now they are not able to come back here again. So new layer will again come up. Like this, this entire will get evaporated and nothing will remain over here. But when we put a cover, then particles have got no other option rather than coming back. Now children, when the equilibrium has been reached, at this stage of equilibrium, if you measure the pressure, what pressure these particles are putting on the wall of this container, that is known as the vapor pressure. That is known as what? Vapor pressure. So again, at this stage of equilibrium, when evaporation and condensation are occurring at the same rate, at this stage, particles which are in the vapor form they are colliding with the wall of the container, and now whatever impact they produce, that is known as the vapor pressure. So, see you children now in the next video, where I am going to discuss with you Raoult's law and lowering of the vapor pressure. In that, we will also be discussing how the number of particles impact the vapor pressure. Okay, children. So, students, after studying vapor pressure, now we will study what is the meaning of lowering of vapor pressure. Children, you know that here if I have taken the liquid and if I am putting a cover on this, then the vapor which are present above the liquid, they will produce some pressure on the wall of the container. So that pressure is known as the vapor pressure. Children, if suppose I am taking pure solvent, for example, I am just taking water. I am not adding urea, I am not adding sodium chloride, nothing I am adding. Pure water I am taking. Now, pure water at room temperature, it will have particles even in the vapor form, and these vapors will produce some impact. That pressure they will develop over there, which is known as the vapor pressure. Now it is pure solvent or pure substance, so I am putting as P1 standard. P1 standard means what? It is the vapor pressure of that component. That only water is there, so it is the vapor pressure of only water. Now children, you will think, why I am taking only that water, only that? Suppose I am adding even some other substance. Say I am adding some acetone over there. Acetone is what? It is also volatile. So these particles will also come in the vapor form. What will happen? More pressure will be generated. Now the higher pressure is coming. But is it coming only because of water? No. Part of the pressure is contributed by water and part of it is contributed by the acetone. So children, here if I am taking only pure water, then what happens? Vapor pressure of this substance, now there is no acetone, only water is present. Now this pressure, this vapor pressure, I can say that it is only because of the water molecule. Hence I am considering this as the vapor pressure of the pure solvent. Correct? Now children, I am taking bit of the urea. Will urea add to the vapor pressure thing? Urea is a non-volatile substance, it's a solid. Being solid, if I am dissolving in the water, what it will do? Urea, after dissolving in the water, the particles of the urea which are on the top region, I will show you both the things in the diagram. Same amount of the water I am taking. In both the containers I am having only water. Only water particles are there, nothing else, only water. Here also water. But here I am taking water plus urea. So this is a solution for me, because it is having two things. What is that one? Solute and solvent. Remember, if you are having a combination of solute and solvent together, then it is known as the solution. If solvent and solute both are present, then it is what? Solution. Only solvent you are taking, only pure water, nothing you are adding, that is a solvent. Now children, in this case, water particles are free to move. But here in case of solution, after adding urea, what happens? These particles will not allow these water molecules to go up. Evaporation has now been restricted because their way has been blocked by these non-volatile urea particles. Urea particles are non-volatile. They will not evaporate. And they will not allow even the water molecule which is beneath it to get evaporated. They will block the way. You look at this one. Here only water molecule are present. So they all are free to evaporate. They all are free to evaporate. So children, if more vapor particles are present, so vapor pressure will be definitely different. And here, since lesser number of the particles are able to present, then definitely vapor pressure is going to be lower, because here there are more number of the particles, they are able to come out. And here their path is getting blocked. Their path is getting blocked because of these solute particles. And hence, vapor pressure of the pure solvent is higher and vapor pressure of this solution is lower. Children, this is known as the lowering of vapor pressure. Understood? Vapor pressure here, when only water was present, there was nothing to block its way. So large number of the vapor, these molecules, water molecules, were able to come out in the vapor form, and large number of the vapor particles are there. So a higher pressure is generated. But here, since the way the path has been blocked, henceforth, number of the particles in the vapor form is lesser. And lesser the number of particles, lesser will be the vapor pressure. So, both the cases I am taking solvent as the water. But when I am adding a solute, then its vapor pressure has been reduced, lowered. This is known as the lowering of vapor pressure. So after this, children, now we will be studying Raoult's law. So children, now let's study relative lowering of vapor pressure. If suppose vapor pressure of the pure water is P1 standard, and after adding a non-volatile solute like urea, vapor pressure has reduced, so I am taking this as the P value. Now lowering means change in the vapor pressure, delta P. Delta P means what? Change in the vapor pressure. Now change in the vapor pressure we can now write as P1 standard minus P, higher value minus lower value. This will have higher value and this is going to have the lower value. So this difference tells you, yes, this much is the lowering of vapor pressure. Now children, after studying lowering of vapor pressure, you will also come across a term known as the relative lowering of vapor pressure. Now lowering of vapor pressure we have understood. Then what is this relative lowering? Let's try to understand what is the meaning of relative lowering of vapor pressure. This I will explain you with one example. If children, if suppose one person is going to purchase something and the seller has reduced 10 rupees. How much he has reduced? 10 rupees. He came at home, he is saying, yes, I did that, I purchased this thing, and I asked him, I did the bargaining with, and he has reduced 10 rupees for me. Then of course, people at home, they become very happy. They asked him, what was the cost, the thing you purchased? He told that cost of the thing was, say, 20 rupees. Everybody became very happy. Oh, very good. Cost was 20 rupees, but because of your argument, bargaining and all, he has reduced to 10 rupees. Very good. Fantastic. Next day also you go and purchase. Think. Same person, some other day, went to purchase a flat, house. And the cost of the house was 40 lakhs of rupees. Again he came back at home. He told, yes, I did the good bargaining. Yes. What happened? Yes, he has reduced the price. How much? 10 rupees. My God. In 40 lakhs, 10 rupees is nothing. But when he was purchasing some other thing, maybe potato, and he has got reduced price, 10 rupees, reduced the price, it was having a big impact. So children, this is known as a relative. In a 40 lakh business, 10 rupees is having no significance. But in a 20 rupees ka business, that 10 rupees is having a large impact. So relative lowering. Here, relative lowering means what was the original vapor pressure and now how much it has been reduced is known as the relative lowering. Again, relative lowering, if I have to write, I will write this delta P lowering divided by what? Divided by original vapor pressure of the pure solvent. If suppose delta P is the change, delta P is the lowering, this much is the vapor pressure has been reduced. Vapor pressure has been reduced by this value. What was the original vapor pressure? Now it is having a great impact. Just like our example. 10 rupees का profit in a 20 rupees का business is actually 50%. But 10 rupees का profit in 40 lakhs of rupees is nothing. So here we come to know the relative lowering of vapor pressure. And next we will be starting with the Raoult's law. So children, let's begin with Raoult's law. Here, if suppose I am taking one substance having vapor pressure P1 standard, any volatile substance suppose I am taking, and its vapor pressure is P1. Similarly, another substance I am taking having vapor pressure of P2 standard. Children, whenever we are adding standard, it means that only one component is present. Now they are not solution, they are the pure component. Only suppose these two components we have taken. Now in another container, few moles of this one I am putting, say x1 mole of this substance. I will give it another symbol, say like this. X1 is present, and this I am taking as x2. Another set, so you can identify. One part is what? X1, and another is x2. Particular mole I am taking. Now children, this substance here is producing some vapor pressure. Another one is producing some vapor pressure here. Children, when I am adding both of them, and both of them are here volatile. Both of them are what? Volatile. Volatile means what? They get evaporated fast. If I cover from here, now the vapor pressure over here, tell me, what do you think? From here to here, this one will be lesser or higher? Think. This is volatile, having some vapor pressure. This is volatile, having some vapor pressure. If I am adding both of them are volatile. They are not like urea, which is not getting volatile, which is not able to come out in the vapor form. These both liquids are what? Volatile. And both these liquids will add to the vapor pressure. So here we are going to observe the higher vapor pressure. Both of them are now contributing. So both of them are since contributing, so vapor pressure will be higher. Now question comes, how much contribution each of them are making? Is it same? Is it equal or different? So now question is what? How much contribution each of them is making towards the total vapor pressure? I will say total vapor pressure. Then answer for this is given by Raoult's. According to Raoult, contribution by P1 will be equal to mole fraction. What is that? Mole fraction of P1 present into P1 standard. If suppose you have taken 0.5 mole fraction means what, bacha log? What is the meaning of mole fraction? Out of every 1 mole of this solution, how much mole is of X1 and how much is of X2? Once more, if I am taking 1 mole of this substance, how much? 1 mole. Then this one may be present up to this much level, that one may be present to the higher level, or both of them may be 50-50%. It is up to me. It is up to the person who is doing the experiment. Like, if suppose 1 rupee is given to me, 50 paisa I am expending for something, 50 paisa for something else. So this is known as the fraction ka concept. Of course, 50 paisa, suppose children's, 100 rupees has been given to me. Out of that 100 rupees, 20 rupees I am taking this pen. 20 rupees I am taking ink. 40 has gone. 60 rupees I am putting in the bank. 10 rupees I am donating. 50 rupees I am putting in the bank. So out of every 1 rupee, I can say 20% has gone for the pen, 20% has gone for the ink, 10 rupees means 10% donated, and 50% has gone in the savings. So children's, this, when you talk, large number of things are there, but when you discuss for one, then it becomes a fraction. Of course, I may be having 10 mole, 20 mole, 100 mole, whatever. But when we discuss for 1 mole, then it becomes a fraction. If every 1 mole is containing this much, then 10 mole will contain how much, that I can easily calculate. Hence, we talk in the terms of mole fraction. So children, here, mole fraction, whatever is the mole fraction, into vapor pressure of the pure component will be the contribution of the first volatile substance, which is P1. Contribution of the first volatile substance. Similarly, this substance B, if this is A substance and this is B substance, substance B is having X2 ka mole fraction. P2 is its vapor pressure when it is present alone. P2 is what? Vapor pressure when only this substance B is present. P2. So this is going to be the contribution of this substance B. This is going to be the substitution of the, this is going to be the contribution of the substance A. So the total vapor pressure, I will write here, total vapor pressure is actually contribution of the first substance and contribution of the second substance. Contribution of A and contribution of B. Contribution of the A will be mole fraction into vapor pressure of that pure component plus X1. Now it is X2, we have taken X2 mole for P2 and P2 is standard. Children, since we are now discussing for mole fraction, so remember X1 plus X2 is always what? 1. Yes? For example, I am telling, out of 1 rupee, if 50 paisa has gone for this work, 20 paisa has gone for this work, 30 paisa gone for this work, if I add all, it will become 1 rupee. Same thing, these are the mole fractions. Means we are discussing in terms of 1 mole. So x1 and x2, that becomes total. If you add, it will become 1 mole. Out of every 1 mole, say 50% A is present and 50% B is present. Or some other student, if he is performing the experiment, he may take A as only 20%, B as 80%. But whenever you add, it becomes 1. Like that, x1 plus x2 will become 1. Now children, I can now write x2 as 1 minus x1. I can now write x2 as 1 minus x1. So here, P total is x1 P1 का standard plus x2 I will write as 1 minus x1 into P2 का standard. So P total x1 and P1 standard you write as it is. Now it is in the bracket, so open the bracket. 1 if you multiply here, what are you getting? P2 standard. If you multiply here, what are you getting? P2. Here you will be getting x1 into P2 standard. Very simple. Replacing x2, you can write here x1 plus x2 as 1. So x2 equals to 1 minus x1. And replace it. So P total is now x1 P1 standard, x1 P2 standard, and P2 standard I will take all x1 terms together. x1 P1 standard minus x1 P2 standard plus P2 standard. Now total is going to be, take x1 common, P2 as it is. What I will do, I will write P2 first as it is, no problem for this, only for this much part. P1 standard minus P2 standard and take x1 as common. Yes? Children, any solution which obeys this law is known as the ideal solution, and this law is known as the Raoult's law. Known as what? Raoult's law. So after this discussion, let's see what is the Raoult's law. The partial vapor pressure of any volatile component, this P1, he is talking about this P1. The partial vapor pressure of any volatile component is the product of two things: mole fraction of that component present in the solution and the vapor pressure of pure component. Again, the partial vapor pressure of any volatile component is the multiplication of product of two things: mole fraction of that component present in the solution and vapor pressure of pure substance present in the solution. The substance which is present in the solution, what is the vapor pressure when it is present alone, is known as the vapor pressure of the pure substance. Here the wording: the partial vapor pressure of any volatile component of a solution is the product of vapor pressure of that pure component and mole fraction of that component present in the solution. So revise these things, children. We will be meeting in the next video. with the new concepts. Thank you everybody. Take care.